the last lecture, we have seen the theory and principle behind rotational spectroscopy. In this lecture, we will discuss in brief the principle of rotational spectroscopy, then we will go to rotational Raman spectroscopy, and also we will discuss the application of rotational and rotational Raman spectroscopy. In the last class, we discussed about operators. There are two different operators, kinetic energy operator and potential energy operator. These two are used to calculate your energy of the different rotational levels. Just to summarize, kinetic energy operator is your this double differential, and potential energy is your simply you multiply by VR. If you do that on a wave function, rotational wave function, you can get the energy of different rotational levels. So, energies of different energy level can be obtained by solving wave equation, which is known as Schrodinger equations. So, this is your kinetic energy operator, this is potential energy operator. When they are applied on the wave function, what you can get is energy of the rotational levels. So, solution of this equation can give you wave function and energy associated with different levels. For 3-dimensional rigid rotor, your Hamiltonian will be given by this equation. Since this is a rigid rotor, and so R is constant, and it means that your wave function is a function of theta and phi, and that is called spherical harmonics. And when you apply Hamiltonian on a spherical harmonics, you can get the energy of 3-dimensional rigid rotor. The way we solve this equation is, first we divide this wave function as a multiple of two functions. One is a function of theta, another is function of phi. And when you do that, you will get these two equations, and solution of this will give you your this function of theta and the function of phi. And when you multiply these two, you will get the spherical harmonics. So, solution of the second equation, which we discussed last time, is your this 1 by root 2 pi exponential I m phi, and so you can see that there is one quantum number required, that is called m, where m can take only integer values, and m is equal to 0, plus minus 1, plus minus 2. The second wave function, which is a function of theta, can be obtained by solving this differential equation, and the solution is given by associated Legendre polynomial. So, now we derive phi part of the wave function and theta part of wave function. So, a spherical harmonics is basically multiple of these two wave functions, and the value of these are given for different value of your L and M or J or M. So, if J is equal to 0, M is equal to 0, then you have a spherical harmonics has the value is equal to 1 by root 4 pi, and similarly when J is equal to 1, your M is equal to 0, then you will get this function. So, in some situation this is independent of theta for a particle value of J and M, sometime it is function of theta and sometime it is function of theta and phi. So, once you know wave function, we also know what will be the Hamiltonian. Hamiltonian is generally given in terms of momentum operator. Momentum operator is square divided by 2y, and momentum, when you apply this operator on wave function, you can get momentum value, and that is h bar under root j plus 1, and energy is obtained when you apply Hamiltonian to the wave function, and that is equal to h bar square by 2y j plus 1. So, this is for your diatomic molecule. but for different other kind of molecule we can similarly obtain your linear momentum and energy. Hamiltonian can be expressed in this formula, where you have you see in this molecule your IA, IB and IC is different, and so you have a formula where Hamiltonian in axis A, Hamiltonian axis B and Hamiltonian in axis C. So, your Hamiltonian will be sum of these three part. For a spherical top, since IA is equal to IB is equal to IC, your Hamiltonian can be just given by operator L square divided by 2I, and ER is simply h bar square by 2I JJ plus 1. For Prolet symmetric top, IA is less than IB and IC, IB and IC is equal. So, Hamiltonian can be written like this: operator LA square divided by 2 IA and then LB square plus LC square divided by 2 IB. So, here your moment of inertia along B axis and C axis is equal, and this can be written as L square minus LA square. So, L square is basically your operator LA square plus LB square plus LC square. LB square plus LC square will be equal to L square minus LA square, and that is what is done here. And then a Hamiltonian can be written like this, and this value we already know. This is h bar square by 2 IB JJ plus 1, and then your for these two terms we can write another quantum number k. So, this is equal to k square h bar square 1 by 2 IA minus 1 by 2 IB. Similarly, we can obtain energy for oblate symmetrical top. In this kind of molecule, IA is equal to IB, but this is less than IC. So, IC is greater than IA and IB. So, similarly, we can calculate Hamiltonian, and once we know Hamiltonian, then we can get the energy term, and that is simply h bar square by 2 IB JJ plus 1 plus k square h bar square into 1 by 2 IC minus 1 by 2 IB. It is similar to what we obtained for Prolet symmetric top. So, this is all about what we discussed last time. Now, we will go to application part, application of rotational spectroscopy. So, one of the most important application of rotational spectroscopy is determination of bond length. From the rotational spectra, we can measure B, and we know that B is inversely proportional to I. B is your rotational constant and it is inversely proportional to I. I is moment of inertia, and I is given by reduced mass multiplied by R square, where R is your bond length. These two relations we can calculate a bond length. So, for example, if we take CO molecule, we can calculate CO bond length if we can obtain rotational spectra of this molecule. From the rotational spectra, what was observed that B is equal to 1.921175 centimeter inverse, and by putting this into equation I is equal to h by 8 pi square B c, we can obtain your value of I, and from I we can calculate your R, since mu is equal to your 1.1386378 into 10 to the power minus 26 kg. So, if you can measure rotational constant from rotational spectroscopy, you can calculate moment of inertia, and since moment of inertia is related to bond length can be calculated, and that is what we have done in this example. From this, the CO bond length is calculated to be 0.1131 nanometer. Now, this is for diatomic molecule. but for other kind of molecule, the I is not a simple function of r, it is a function of two different distance or one distance and angle, and this is basically given here. Diatomic molecule, you can see this is only function of r, but for linear molecule which has two different distances r and r dash. So, distance between atom A and B is r and atom B and C is r dash, then your moment of inertia can be written like this: m a r square plus m c r square plus this whole term. Now, you can see that apart from mass, this moment of inertia is a function of r and r dash. So, from simple one rotational constant, you cannot calculate your bond length. Similarly, for symmetric rotor of this type, you can see that is a function of r and theta, and similarly you can have a different kind of rotors, and for different kind of rotors moment of inertia will be different, and these are the equation which is given here. Again you see I perpendicular and I parallel can be given. So, if there is more than one variable on which moment of inertia depends, then what will you do? The one thing which is done is to do isotopic substitution, and good thing is once you do that and see the rotational spectra of that isotopic molecule, then not only you can get bond length, you can also calculate bond angle. For example, for this linear rotor, I just told you that moment of inertia is function of r and r dash. So, one of the way to get r and r dash is to obtain rotational spectrum of molecules, suppose ABC and ABC star. C star is basically isotope of C. Everything is same, r and r dash is same, MC differs, and you know what is the MC. Then you have a two rotational constant, and your moment of inertia is variable of two functions. So, you have a two constants and two functions, two unknowns, and so you can calculate r and r dash. And similarly, if your moment of inertia is a function of r and theta, you can get r and theta by isotopic substitution. So, next we will discuss what is the effect of isotope substitution. For example, if we go from 12 carbon 16 oxygen to 13 carbon and 16 oxygen. So, here we are going from one isotope 12 C to 13 C. So, we know that B is inversely proportional to I, and since I increases when you go from 12 C 16 O to 13 C 16 O, and so B is going to decrease, and once B is going to decrease, and then you can see that the difference between different energy levels is also going to decrease. So, this is your rotational energy level of 12 CO, and this is your rotational energy level of 13 CO, and you can see that here the energy difference is greater and here energy difference is small. And so, your peak or spectra of this isotope 13 CO will come at a smaller B value, So, you can see the shift is towards left hand side. So, apart from giving the value of r and r dash or r and theta, the isotopic substitution can also help us in two different things. One is to calculate isotopic mass accurately within 0.02% of other methods, and then second is isotopic abundance from the absorption relative intensity. So, just we calculated from the rotational spectra, what people saw is 12 for 12 CO, your rotational constant is 3.84 3 to 5 centimeter inverse, and from 13 CO it is this value. Now, this can be used to calculate accurate mass of your 13C. So, the second application of rotational spectroscopy is to get precise atomic weight of isotopes. B value, we know that it is inversely proportional to I. So, if you take two isotopes, for example 12C and 13C, then your B1 by B2 will be going to I2 by I1, and since I is mu r a square, and if we assume that bond length does not change, if I change 12C by 13C in CO, then you can simply write it is I2 by I1 is equal to mu 2 by mu 1. B is basically inversely proportional to reduced mass. So, reduced mass of the second component can be calculated by simply B1 by B2 into mu 1. So, if I take the example of 12C 16O and 13C 16O, so mu 2 means reduced mass of 13C 16O will be given by B1 by B2 into mu 1. We already know B1 by B2 is 1.046. This is obtained from rotational spectroscopy, rotational spectra of 12C 16O and 13C 16O. So, this is 1.046, and then this is your mu of 12C 16O, reduced mass of 12C 16O. And if you put in this equation, you can get accurate mass of 13C. You can get accurate mass of 13C, and that is 13.0007. Then the next application is, again this is related to isotope effect, that you can also measure relative abundance of isotopes. So, suppose there are two molecules in a sample AX and A star X, where A star is your isotope of A, and if we see the spectra of this sample, and what we found out that intensity of rotational lines of A star X is x times that of A x, then we can calculate natural abundance of A star X, and that is given by this equation, y is equal to x divided by 1 plus x into 100%. So, now we will see how to calculate relative abundance of certain isotope in a molecule by looking at the rotational spectrum of the molecule. So, in the given example, it is given that H35Cl, so hydrochloric acid, where chlorine is in the isotope form 35Cl, it shows rotational spectrum peak which is 3 times intense than the H37Cl molecule. So, now we have to calculate what is the relative abundance of 37Cl in the molecule. So, relative abundance of 37Cl can be calculated by using this method, where x is the intensity of molecule with the isotope with respect to the H35Cl, with respect to H35Cl. So, y will be given by x divided by 1 plus x into 100%, and since it is given that H35Cl has 3 times more intense peak than H37Cl, what does that mean is H37Cl intensity, peak intensity is 1/3 of H35Cl peak intensity, and so x is equal to 1 by 3, and if you put x is equal to 1 by 3, what you are going to get is 25%. So, just by looking at the intensity of different peaks in the rotational spectrum, we can calculate the relative abundance of the isotope. There are other applications of rotational spectroscopy. Rotational spectroscopy is quite often used for chemical exploration of interstellar bodies, and for that radio telescopes are used. They detect different chemical species like new and existing molecules and free radicals, and then they also help us in a study of composition of different chemical species. So, first indication of interstellar body comes by looking at calcium 2 plus lines in a spectrum of double star delta Orion. Okay. And later existence of highly unstable species was confirmed using rotational spectroscopy. It has also been seen that few molecules are discovered in the interstellar bodies which were not seen in the experimental methods, but when you find out okay, this molecule can exist, then people went back to lab and tried to confirm those molecules, and they were able to see those molecules. So, cumulative studies with other techniques were also used to find out different chemical processes in interstellar bodies. So, this is different kind of molecule which has been detected by radio frequency or rotational spectroscopy. So, there are whole lot of molecule which was found in the interstellar bodies. It is from diatomic to 13 atomic molecules, and the list is given here, and that is taken from modern spectroscopy book by Hollas. There are other planets or stars has been studied for their chemical composition, and this is cyanodiacetylene. This was found to be in the emission of your Sagittarius B2, and these are your spectral lines corresponding to 1,0 transition, and that is how it was found out that in emission there is presence of cyanodiacetylene. Similarly, rotational spectrum of Orion Nebula has also been carried out, and this is adapted from Astrophysical Journal, and here you can see that there are different kind of molecules like SC3N, S2CO, SO. So, you see this is from 208 to 232 gigahertz, and then 234 to 262 gigahertz. So many molecules can be seen in the rotational spectrum of Orion Nebula. Similarly, SDO and methanol is detected. These molecules are detected in the Comet Hyakutake, and you can see this is the methanol. This peak is corresponds to methanol, this peak corresponds to SDO, and this again peak correspond to methanol. So, different kind of species contribute to different kind of planets, comets, stars. Rotational spectroscopy is one of the very important tool to know the composition of these emissions. It has been used for determination of temperature. So, intensity of rotational spectrum is proportional to temperature. If you remember that intensity is related to number of atom in ground state and excited state, and Boltzmann distribution depends on temperature. So, intensity of rotational spectrum also depends on temperature. So, temperature of interstellar bodies can also be determined using rotational spectroscopy. High temperature reaction can also be studied. Now, next application of rotational spectroscopy is in obtaining dipole moment of the molecule, and we already know from the Gauss selection rule of rotational spectroscopy that only molecule that possesses permanent dipole moment will show rotational spectra. Dipole moment is separated charge into distance. So, the dipole moment can also be calculated by rotation. What we do is, generally we see the effect of effect of electrical field on the rotational spectroscopy, and that is related to dipole moment, and that is known as Stark effect. If you remember that rotational levels are degenerate, and degeneracy is given by 2j plus 1, but this degeneracy is lifted in presence of electrical field, which is known as Stark effect. And these levels, so j is equal to 0, j is equal to 1, j is equal to 2, 3, 4, they split into j plus 1 level. So, for example, if j is equal to 2, then it will split in 3 levels. If j is equal to 3, then it will split into 4 levels. And this is your Stark effect on j is equal to 3 to 2, your rotational spectrum of OCS molecule. And this splitting is dependent on dipole moment. Okay. So, in absence of electric field, we know that energy is given by h square by 8 pi square I j j plus 1, but in presence of electric field, particularly for linear molecule, there is one more term here comes. So, in absence of electrical field, your energy is not dependent on m, but in presence of electrical field, energy is dependent on not only j, it will also be dependent on m. And here mu is your dipole moment, E is electrical field. So, by studying Stark effect, we can obtain the value of mu. So, this is the way dipole moment is calculated. There are other applications, differentiation between conformational isomers, and conformational isomers will have different dipole moment if they are polar, and on rotation bond length will remain same, but direction of permanent dipole moment changes. So, everything is same, only thing is your dipole moment is different, and so we can know from the rotational spectroscopy which conformational isomer exists. So, I will discuss one paper, shape of leucine has been seen in the gas phase. So, this is your skeleton of alpha amino acids, and based on different intramolecular hydrogen bond, 3 conformation has been considered. 3 conformation has been considered, 1, 2 and 3. This is called cis COH, trans COH, and this cis COH, but you can see here that this H is like here this H, this 2 H, and then here H is like this, but now here there is a flipping. So, these 3 different kind of amino acid skeleton you can think of with different molecular bonds. Now, we can again think of each of this 1, 2, 3 isomer can exist as A, B and C depending on rotation about C alpha and C beta bond, C alpha and C beta bond. So, you see C alpha C beta bond, this is C alpha C beta, C alpha B, this is C alpha behind, and this is your C beta, the upper one is C beta, lower one is C alpha, and this is C gamma. So, here you can see the angle is 180 degree. In this again you see this is C alpha, C beta is the upper one, and C gamma here. This angle is your 60 degree, and here your C alpha, which is below the plane, C beta is up the plane, and your C gamma is here. This is your minus 60 degree. So, these 3 conformation you can think of, these are lower energy configuration, and they are generated by rotation around C alpha C beta bond. Similarly, C beta and gamma. So, again there will be 3 different angles, 60 degree, minus 60 degree, 180 degree. So, you have C gamma. So, you see this is the H gamma, then this is C gamma, and then below one will be C beta, and this is C alpha. This angle is your 60 degree. Similarly, minus 60 degree and 180 degree. So, these are low energy configuration generated by the rotation around the C beta C gamma bond of leucine. So, in effect there will be 3 into 3 into 3, 27 different kind of conformation which you can think of, which are lower energy configurations. So, total of 27 conformation, and then they did ab initio calculation and they find out that out of this 27, your 9 is the lowest energy conformation, and they have given the name 2A, 1, 2, 1B, similar like so. 2 is your based on hydrogen bonding, the A is based on rotation around C alpha C beta bond, and this 1 and this is 2 is based on your rotation around C beta C gamma bond. These 9 lowest energy conformations, they calculated your rotational spectra, they calculated rotational constant, and these are the different rotational constant A, B, C. They calculated electric dipole moment, they calculated nuclear dipole moment. So, these are all theoretical calculations. So, they obtained the rotational spectra of leucine, and what they are able to find out is there are only 2 conformations. They can find only 2 conformation which is basically your populating the leucine in the sample, and that is called 2B1, that is 2B1, and this is your 1B1. And you can see here that for this 2B1, these are the values which has been obtained by rotational spectroscopy. 1B1, these are the value for rotational constant, these are the values for dipole moment, and this is value for nuclear quadruple splitting. These are the values for, and this is the one which they obtained from the theoretical modeling, and you can see that A value 2008 97, and you see 2870, 844, 838, 768, 770, and for 1B1 2756, A, B value is 853 and C value is 802. So, now by matching experimental with the theoretical calculation, they are able to predict that leucine exists in 2 different forms. One is 2B1 and another is 1B1. Conformation can be differentiated by obtaining your rotational spectrum. Another application is, which is well known application, is microwave. Okay. Its mode of operation depends entirely upon the absorption by the food of microwave radiation. So, how food gets cooked is like this. Microwave radiation is absorbed by water molecules. So, these are the water molecules, and they basically absorb the microwave radiation, and what they do is, when it is trying to come to ground state, they do is by non-radiative emission. What does that mean is it releases heat and then it comes back to ground state. This heat is used to cook your food, So, the microwave that penetrate the food have an electrical field that oscillate your 2.45 billion times a second, a frequency that is well absorbed by polar liquid molecules such as water, sugars, fats and other molecules. This water interacts with microwave, they go from your ground state to higher excited state, they flip their orientation, they rotate very rapidly, they bump into one another, and that is how they produce heat which is used for cooking the food. Glass, paper, ceramic or plastic containers are used in microwave cooking because the microwave pass through them, but matter reflects microwaves, and that is why it is not safe to use metal pans or aluminum foils in oven, may even damage your microwave. Okay, so next application is used for chemical analysis. So, these methods are quite used to know the different chemicals. Only disadvantage is molecules must be in gaseous form, or it can be converted into gaseous form, then only you can study that. This gas phase reactions is rotational spectroscopy is particularly important for gas phase reactions, because they do not follow well behaved guidelines. So, microwave spectroscopy is particularly used for this kind of studies. Now, the next thing which we are going to discuss is a scattering spectroscopy. These are particularly important if you want to calculate energy of rotational level for nonpolar molecule. These are basically based on a scattering phenomenon, and scattering can be of two types. One is elastic scattering, where wavelength of a scattered light is same as that of incident light, and the second is the inelastic scattering, where wavelength of a scattered light is different from that of incident light. So, this is your elastic scattering. So, you can see this is energy gap is same for both your incident light and a scattered light, and so lambda is going to be same for the scattered light and incident light. But in inelastic scattering, energy gap is going to be different for the emission and your scattered light, and in this case your lambda is going to be higher for a scattered light in comparison to lambda of your incident light. But in the next case it is going to be different. Again, elastic scattering can be of two types. One is Rayleigh scattering, where a scattering intensity is independent of a scattering angle, and in this case your intensity is proportional to 1 by lambda 4. Intensity is proportional to 1 by lambda 4. So, are inversely proportional to lambda 4, whereas big particle scattering, where a scattering is dependent on a scattering angle. So, in Rayleigh scattering your scattering only depends on wavelength, but in big particle scattering your scattering intensity is dependent on both lambda and your scattering angle. So, this is your ground state, and there is a first excited vibrational level. So, here is the incident. If light is incident, it goes to higher excited level, and then you see. So, this is your Rayleigh scattering. So, lambda of incident ray is similar to lambda of your scattered light. In inelastic scattering, most important one is Raman spectroscopy. It is a type of inelastic scattering. So, if the energy of a scattered light is lower than incident light, we get Stokes lines. So, there are two different kind of Raman spectroscopy. One is your Stokes scattering, two different kind of scattering in Raman spectroscopy. One is Stokes scattering and another is anti-Stokes scattering. So, in anti-Stokes scattering your lambda is going to be lower, whereas in Stokes scattering your lambda is going to be higher. So, what we generally calculate is what is the difference between your peak and your for laser peak. So, if energy is scattered light is lower than that of incident light, we get a Stokes line. If the energy of scattered light is higher than incident light, we get anti-Stokes line. So, this is theory of rotational Raman. It is basically property of the sample which determines a scattering is polarizability. So, the factor on which a scattering depends is polarizability of the molecule, not the dipole moment, as we seen for rotational spectroscopy. So, what is polarizability? It is a measure of the degree to which electrons in the molecule can be displaced relative to the nuclei. So, when monochromatic radiations falls on molecular sample in the gas phase and not absorbed, then your scattering can happen, and oscillating electric field of radiation induces electric dipole in the molecule, and this electric dipole mu is given by alpha into E. E is your oscillating electric field and alpha is polarizability. If suppose magnitude of E is given by this formula, A sin 2 pi C nu bar into T. Okay, so, this is your frequency, this is frequency of incident radiation. Now, once it falls, it interacts with electric field interacts with polarizability. Polarizability will be given by this formula. Alpha is equal to alpha 0 r plus alpha 1 r sin 2 pi 2 mu rotational into T. Now, this 2 factor comes because of during rotation polarizability becomes same twice. Polarizability becomes same twice in 360 degree rotation, and so you can calculate mu. So, alpha is this value and your this is E. There is a multiplication of the 2 sine terms, and we know that from 2 sin A into sin B is equal to cos A minus B minus cos A plus B, and that gives you 3 different terms. If you multiply this alpha into E, you will get first term. The second term you can see this is nu bar plus 2 nu bar rotation. Okay. So, here your frequency is increasing, and then this is third term is nu bar minus 2 nu bar rotation. So, first term is Rayleigh scattering, second term is your anti-Stokes line, and the last term corresponds to Stokes-Raman scattering. So, you see cos A minus B minus cos A plus B. So, this is your cos A plus B and this is your cos A minus B, cos A minus B. So, this is your typical rotational spectra. In this diatomic or linear polyatomic molecule, your Gauss selection rule for rotational Raman scattering is delta J is equal to 0 plus minus 2, and this is wave number. So, this side is your anti-Stokes line, this side is Stokes line. So, in your anti-Stokes, delta J is equal to your minus 2, where for Stokes delta J is equal to plus 2, and delta nu bar means difference between this side or this side is given by f j plus 2 minus f j, and delta nu bar is 4 b 0 j plus 6 b 0. So, it will depend on anti-Stokes, then it will be towards this side, and your for Stokes it will be towards right hand side. So, instrumentation of Raman spectroscopy, it is very important. Raman scattering is very weak phenomena. So, incident radiation should be highly monochromatic, and that is why laser is used as a source. So, this is your typical experimental setup for your Raman spectroscopy. Different lenses are used to focus incident ray back to the sample, and initially lasers are used where in UV vis region. The most commonly used was helium neon laser, which has wavelength of 632.8 nanometer, and then argon ion laser which has wavelength of 514.5 nanometer. But problem with this kind of lasers are that many molecules absorb and fluoresce in visible region, and the fluorescence will mask the much weaker Raman scattering. So, next came is IR lasers. Good thing is that you can avoid the problem of fluorescence, but bad thing is since we know that scattering is basically proportional to 1 by lambda 4. So, it is basically decreases, Raman scattering decreases rapidly with increase in the wavelength, and so detection becomes extremely difficult since signal to noise ratio is very low. to avoid this problem, people started using FTIR laser. Again, FTIR is generally used for the low sensitive technique, and here again it can provide intensity advantage. A single spectrum can be obtained rapidly, and you can take more number of scan and then you can add up to get appreciable intensity. Application Raman spectroscopy. Raman spectroscopy is less restrictive than pure rotational spectroscopy, since here you do not have to think about whether it is a polar molecule or not. Linear symmetric molecule does not show rotational spectra, but linear symmetric molecule shows rotational Raman spectra. Raman spectra can be used as a compound fingerprint, hence it is useful technique for identification of many compounds. This is a non-destructive technique which makes it a better option for analysis of biological sample. In biological samples, more than 50% water is present, which is a weak Raman scatterer, and usually do not interfere with the Raman measurement, which is not the case in the IR kind of measurement. They can be used to distinguish between cancerous tissue from normal tissue, and people have used is to differentiate malignant tumors from normal breast tissues, and it has also been used to look at neoplastic changes in a mouse model. So, in this lecture we are able to see the theory of rotational spectroscopy and rotational Raman spectroscopy, and also we have looked at the application of this spectroscopy in both chemical analysis and biological analysis. So, in the next class we will discuss the infrared spectroscopy. Thank you.